So we use Gauss elimination methods to be able to solve the linear algebraic equations like in this form. If n, the number of equations, is smaller than or equivalent to 3, we can use graphical method, Cramer's rule, and elimination of unknowns. If the number of equations is greater than 3, then these will be still can be used, but will be very time consuming and difficult. That's why there are further advancement of this elimination of unknowns as the naive Gauss elimination and full Gauss elimination, which also includes some pivoting and scaling. We will show them, and also Gauss-Jordan method. So we will show all of these in the following slides, starting with the graphical method. The graphical method is usually useful for two equations. For instance, here we have two equations, and we can here isolate x2 for both. x2 isolated here, you can see, and we just want to actually draw these into a curve, into a graph actually, as the straight lines, because these are only like two equations, and with linear form this will create straight lines. So x2 slope, this is the slope, and the intercept. From here we will have two lines, and the intersection of these two lines will give us the results of x1 and x2 in the Cartesian coordinates. Yeah, the intersection of the lines represent the solution of x1 and x2. So if we have three simultaneous equations, on the other hand, it will be a little bit more complicated, but still we can use this graphical method. Each equation would be represented by a plane, straight plane, rather than a line, straight line, in a three-dimensional coordinate system, and the point where the three planes intersect would represent the solution. Beyond three equations, graphical methods break down and consequently have little practical value for solving simultaneous equations, because we cannot really represent more than three equations in a graphical format. In this slide, we will solve an example to be able to learn about the graphical method for two equations. Here you can see the equations. One is 3x1 plus 2x2 equals 18. Another one is minus x1 plus 2x2 equals 2. So to be able to use the graphical method, we will just simply isolate one of the unknowns in both equations. Here, for example, x2 and x2, we can isolate them. If we isolate x2, for the first one, x2 is equivalent to minus 3 divided by 2, x1 plus 9. And for the second one, x2 is equivalent to 1 divided by 2, x1 plus 1. And if you want to solve these, basically you will need to just use a graphic and draw the lines for these. Let me write or draw a graph over here like this. This one is x1, this one is x2. So for the first one, if x1 is 0, then x2 is 9. And for the second one, if x1 is 0, x2 is 1. We can simply use these starting from 0. So let's write down some numbers here. This is 2, 4, 6, 8, and 9 maybe. And the first equation, for example, starts from 9, and we can actually try different values as well. For example, x2 is 2, then x1 is 2, then x2 is 6. You can see if this is 2 minus 3, 6. So between these we can draw a line. So for x1 is 1, it's here. x2 is 9, and for x1 is 2, 4, 6. If x1 is 2, then x2 is 6. maybe somewhere here. So if we continue, if x1 is 4, x2 is 4, 6, 3. If x1 is 4, x2 is 3, like here, maybe. So we will just draw a line passing through these values. This line will be the plot of the first equation. Let me just try to make it straighter, but that's not possible. We can do the same for the second equation. For that, x1 is 2, then x2 is 2, x1 is 4, then x2 is 3. So let's draw that by red maybe. If x1 is 0, then x2 is 1 here, this point. x1 is 2, x2 is 2, this point. And x1 is 4, x2 is 3, regular this point. So we found actually the intersection by chance. You can see this one is the second equation and first equation. So intersection of this will give us the result here, meaning that this is x1 and this 3 is x2 for the solution. So intersection x1 is 4, x2 is 3. Then we can check if these are correct by simply substituting these to the equations. For example, 3 times x1 is 4 plus 2 times here for the first equation, x2 is 3 equals 18. We see that 18 equals 18. Then this is correct. Similarly for the second one, minus x1, which is 4, plus 2 times 3 equals 2. Then 2 is 2. This is correct too. So this is very easy using the graphical method. If we have two equations, it's very easy to find the intersection as the roots. You can see here. The graphical method is useful for especially two equations, but there are still cases that can pose problems, create problems when solving sets of linear equations. So we are showing the three problems here. First of all, the first one, two equations represent parallel lines. You can see actually the two equations are the same. So those brings parallel lines. Actually not the same, but the resulting is different. Here is the same, but this is 1 over 2, for example. They are parallel. If they are parallel, because we are checking the intersection of them, actually there is no solution here. Because there is no intersection. There is no solution because the lines never cross. So this is called a singularity problem. The system is singular. The second one here, the two equations represent the coincident lines. In here, actually, they are almost the same. Actually, in terms of magnitudes, it's the same. This and this are the same, actually. Just here, it's just multiplication of this by 2. That's why the curve is the same. So they are coincident. In here, both curves are intersecting at each point. Infinite number of solutions. Because there is infinite number of intersections, there are infinite number of solutions. Again, this is called singular. So both types of systems, parallel, all coincident, both of them are called to be singular. This singularity problem is really an issue of these sets of equations, because we don't find a single solution for them. The third one is something a little bit different. So there is one intersection, but because the curves are very similar to each other, almost parallel or almost coincident, it is not easy to get this intersection point. Here, for instance, the coefficients are very close to each other. That's why these are very close. You can see. We will not be able to identify the intersection exactly. So these kind of systems are called ill-conditioned. The point of intersection is difficult to detect visually, and ill-conditioned systems are sensitive to the round of errors. So especially these coefficients can be represented in several significant figures, but if we round or cut some figures, there will be some round of errors, and this will guide us to the wrong location. And that's why they are problematic for the numerical solution of linear equations. So we have to be careful about this kind of equations, and using graphical method can have an issue while finding the roots of these as well.